Perfect. Okay. All right, guys. Hello, everyone. Let's get started. We have a lot to do. So I hope you guys are using the Google Classroom. I mean, finding all documents like the recordings too. Tell me if there's anything wrong with this. You will find on the Google Classrooms both homework, which will be graded, and a test, which you will have to do on Saturday morning. So the test is going to be limited time, 3 hours for you to solve, let's say 6 problems, 6 or 5 problems. I will decide. So as I said, the test is 3 hours long only, and then you directly post your answers on the Google Classroom, and they will be graded. And the homework will also be available from Saturday morning, but you will have until Sunday night to hand in your solutions. I'll tell you more about this tomorrow. We still have time. So, okay, so let's get started. Today, guys, let me see. Okay, everybody's not here, but let's get started still. So today we're going to discuss number bases. So, of course, problems dealing with digits of numbers. So which means in base 10, but also in some other bases. Cool. And before we do this, of course, we start by a warm-up. So this time it's going to be about prime numbers, divisibility also a little bit. Okay, so let's get going. Let me zoom in a little. And let's go. Cool. Okay, good. So the first problem, it's an equation. P and Q are prime numbers, both are prime numbers, and we want to solve for this. So please tell me, guys, any ideas you have? What have you tried? What should I do? So of course you need to help me. I'm not gonna solve it myself. So 5p squared minus 2q squared 6 is equal to 6q minus 9p. I have to use the fact that p and q, yeah, exactly, Nicole, thank you. I have to factor, right? So in order to factor, I need to factor by the prime numbers, because this is what's interesting. So let's just factor by the prime numbers. So basically, rewrite the equation after factoring by p. I don't remember. Let's try. So 5p minus plus 9. And on the other side, I would have 2q plus 6 minus 6 plus 6. Okay, perfect. So we have only pluses, which is nice. Only positive numbers is easier to deal with than negative numbers. And now that we have done this, let's try and use the fact that P and Q are prime numbers. So maybe before we do this, I'm just noticing that here we have a factor 2 that I can take out, right? Sorry. So this is Q plus 3, right? I'm not mistaken. I hope I'm not. Yeah. So let's use the fact that P and Q are prime numbers. What can you guys tell me? So first, maybe we can look at the fact that P will divide the other side, right? So 2q plus 3. Maybe we can say this. We can also say that Q divides the other side, 5p plus 9. But there is this factor 2 that maybe we can get rid of. So let's see. P times 5p plus 9 So basically we have two cases. If P is equal to 2, it's probably a case that we can deal with very easily. And then if P is odd, then basically 5P plus 9 will be an even factor. So let's see, should we deal with those two cases? Or, for example, this divisibility is sufficient and we can use it directly. Let me know, guys, what you think. What do you think? P divides 2 times Q times Q plus 3. Okay, so yeah, maybe we can just look at the two cases. Okay, let's do this. Or actually, in general, from this divisibility, P divides 2 times Q plus 3, we can say that actually P divides 2, or P divides Q, or P divides Q plus 3. And I hope you guys remember this. We said that, so this is just because P is prime, right? So P is a divisor of the product of 3 factors. And since it's prime, basically it has to divide one of them, at least. It cannot not divide one of them, it has to. So we actually have those 3 cases to look at. So let's actually do this directly. So first 2 cases are very easy to deal with, because if P divides 2, then what does this mean? And if P divides Q, what does this mean? Those should be easy to deal with. And then for the last one, I cannot conclude directly, but I can write, as we did yesterday, Q plus 3 as P times some K, K being a positive integer. So what do you guys say about the first 2 cases? P divides 2, P divides Q. How can I conclude directly? I mean, at least the value of P. What's the value of P? Yep, exactly, yeah. So if P divides 2, well, 2 is a prime, right? And P is also a prime, so basically there's only one case. And same for P divides Q. P has to be equal to Q because both are primes, right? Okay, so now that I have the value of P, I still have to find the value of Q. So actually I'm not done. I said I was done, but I already have P, so the equation will be easy to handle. Either we'll find a solution, or there will just be no solutions. So let's look. This gives so 2 times 19, right? 2 times 19 is twice Q times Q plus 3. Okay, so Q. Okay, perfect. So of course I can try to solve this, because I only have Q as I mean, Q is an integer, it's a prime number, and Q times Q plus 3 has to be equal to 19. The problem is that 19 is a prime, so this will not happen. So this is impossible, because 19 is prime, right? Okay, this is clearly impossible. And now second case, if P is equal to Q, then I'm left with 5Q plus 9 is equal to twice Q plus 3, right? And now I can just solve this. So what's the value for Q? Can you guys help? Oh, -1. If it's -1, then it's also impossible. Oops. Yeah, if Q is -1, this is clearly impossible too. So both cases are impossible. And now I have to deal with the third case. And I have basically a nice way, I would say, to rewrite Q as pk minus 3. Okay, so if I plug this in, probably I'll be able to finish. So I will still have to find the value of k, but I will be able to finish. So let's rewrite our equation. So this would give p times 5p plus 9 is equal to pk minus 3, and then q plus 3, so actually pk, right, directly, of course. I just try to simplify it. And then what do I get? So 5p plus 9. And on the other side, twice pk squared minus 6k, right? Something like this. Now, what would be nice is to, again, factor by p, because this is always what helps. Factor by the prime number and use the fact it's a prime. So probably this is what I would do. So factor by the prime number, 2k squared minus 5 is equal to 9 plus 6k. Okay, so what can you guys say about this? So actually, I factored thinking, okay, I'm going to use the fact that p is a prime number, but actually I want to do something else. What's the divisibility I can use that is probably going to be very interesting? So p divides 9 plus 6k. I can write it down, but I'm not sure it's going to be useful. But on the contrary, 2k squared minus 5 dividing 6k plus 9. I think this is going to be very useful. Can you guys tell me why? So why do I think this divisibility is interesting and will help us find the value of k? Why is that? What do you think, guys? So let me see, what did you do? Divides 3. So why 3? Abraham, why are you saying 2k squared minus 5 divides 3? Factor out 3 from 6k plus 9. Oh, okay. Okay, I see what you mean. The problem is that what you said here is not correct, because 2k squared minus 5 is not necessarily prime. Okay, so let's make sure this is clear for everyone before we finish. That's a very important reminder, I think. So what we said is that if p is a prime number and p divides a times b, then p has to divide a or p has to divide b, right? But p is a prime number, remember. If p is not prime, if it's about any other number, then it doesn't work. So let n be just any positive integer. Okay. If n is not prime, and but by the same way, n divides a times p, then I can say nothing. Then I have no idea if n divides a, and I have no idea if n divides b. Anything can happen, basically. Let's try and prove this, but I'm going to explain to you why, giving you a counterexample. Okay, at least I think you guys can give me a counterexample. So give me a counterexample where n divides a times b, and n doesn't divide a and doesn't divide b. Okay, can you guys find such a counterexample? Okay, counterexample. Did you guys found one? Oh, you didn't. Why? Oh, okay, good. Yeah, exactly. For example, 18 divides 2 times 9. Of course, because 2 times 9 is equal to 18, right? But then 18 doesn't divide 2, and at the same time, 18 doesn't divide 9, right? Because 18 is bigger than those numbers. Okay, I can give you another example. Um, so what other example can I give you? Actually, any other example will be similar, so we're good. But yeah, this is a very good counterexample, so please do not make this mistake. Let's see if I can give you another reminder, since we're discussing about reminders. Um, well, I think we're good for now. So let's get back to our problem. What were we saying? Yeah, we were saying that 2k squared minus 5 divides 6k plus 9. And I was asking you guys, why is this interesting? And so why is it interesting? Actually, none of those numbers apparently is a prime. So it's not the prime fact that is interesting. But what's interesting is that 2k squared minus 5 will probably be actually bigger, greater than 6k plus 9. Why? Because there is a square. So k squared is much greater than the right hand side, and probably this divisibility will not take place in a usual case, just because the divisor is too big, right? So let's write this down. 2k squared minus 5 divides 6k plus 9. Okay. So, and actually both are positive. So basically this means that I need 2k squared minus 5 to be less or equal to 6k plus 9. And I think this will not happen very often because the square will be too big. So let's find out, when does this happen? Well, this happens if 2k squared minus 6k minus 14, right, is less or equal to 0. So now how can we find the values of k that satisfy this? I can divide by 2 before we continue. Okay, so what I would do here is directly complete the square, because whenever I have a square, it's easier. Otherwise, I could use the fact that this is just a degree 2 polynomial, which looks something like this. Let me see if it has real roots or not, but 9. Yeah, this would be something like this. So it will be negative only in this shaded area. Otherwise, it's positive, right? So yeah, this means k has to be very limited, in a very limited range. So I usually complete the square because it's easier and I'm dealing with integers, right? K is an integer. So k minus, oh, actually, it's going to be a bit hard to complete the square here because I have a 3 times k and not not an even number multiplied by k, right? But still, I can try and do it, and it would look something like that: minus 7 minus 9/4. So please stop me, guys, if you don't understand this part. I'm completing the square by adding 9/4, subtracting 9/4. And then my goal is to basically try to find an easy way of finding the value of k that is possible. So 7 plus 9 over 4. Okay, so I will just multiply by 4, so everything becomes integer. So 2k minus 3, 28, 37. Yeah, thank you. Okay, and now, well, now you can help me, guys. So what's the highest value for k that is possible? Well, 2k minus 3 in absolute value has to be less or equal to 6, right? Yeah, but we said that this was positive. Did we say this? Oh, actually, we're not sure about it, but k will certainly be, I mean, 2k minus 3 will certainly be positive. So what possible values for k do I have here? What do you guys think? What will the possibilities be? 0, 1, 2, 3, 4. Okay. From 0 to 4. Yes, I agree with you. So actually, there are some values for k which will be removed from this set. And I'll tell you why in a second. But yeah, theoretically, all those values for k are possible. But I will remove from this set the values that do not make, let me show you, that do not make 2k squared minus 5 positive. Because in this equation, it is showing that 2k minus 5 has to be positive. Okay, so basically I need to remove the case where k is 0, 1. So those are not possible. And then, yeah, I have 3 cases. This is correct. So I'll let you guys check the cases. But what will happen, I think, is that k is equal to 2 will be the only possible case. So I'll let you check it. And k will have to be equal to 2, and then you guys can finish. If you want, I can give you the values for p and q. So you guys can check. Seven and 11. Okay, cool. So now let's go to another warm-up problem. And okay, so actually, I think since we took a little too much time on the first one, we will skip number 2. So if you have questions about it, please ask at the end of the lecture or during or at the end of problem session. But let's do problem 3 now. So I'm considering 9 integers. Oh, if you want, I can just give you a quick hint on this problem. Try to factor a to the 4 plus a2 plus 1. And if you want, you can ask to solve it together at the end of the lecture. Okay, now let's go on problem 3. Problem 3. I'm looking at a set of 9 integers, okay? And I know that the prime factors are only 3, 5, or 7. So how can I write down those integers knowing this fact? Well, I know how to write their prime factorization, right? So I know that any integer in this set will be written as 3 to the a, 5 to the b, and it was 7, I think, 7 to the c, right? Let me check it. Yeah, 3, 5, and 7. Okay. And now the question is, show that we can always find 2 of those 9 integers such that if you multiply them, the two of them, you get a perfect square. Okay, so first, let's do it. Let's first understand what does a perfect square mean. So of course here, A, B, and C are non-negative. The exponents can be zero because the problem only says the prime factors are among 3, 5, and 7. So we're not necessarily divisible by 3, 5, and 7. I mean, those integers are not necessarily divisible by 3, 5, or 7, but if they have a prime factor, it's either 3, 5, or 7, nothing else, right? So this is why the prime factorization looks like this. And the exponents are not necessarily positive, but non-negative. Okay. Now my question is, what's the perfect square? How would you write a perfect square? Of course, a perfect square which has only 3, 5, and 7 as prime factors. So how would you write it? I mean, what do the exponents have to satisfy so that it's a perfect square? Yeah, exactly. The exponents just need to be even. It's not necessarily the same number. All we need to know is that the exponent is even. That's it. Yeah, perfect. So yeah, quick example. This number is a perfect square, of course. Okay. All right. So now that we have understood this, I'm going to ask you another question. So it looks like a pigeonhole problem. Why? Can you tell me what would the pigeons be? Yeah, 9 integers. I agree with you. And how about the pigeonholes? So the prime numbers, yeah. What does this mean? So every one of those 9 integers is written under the form 3 to the A, 5 to the B, and 7 to the C, as we said, right? Okay, and I'm looking for 2 of them, which would multiply to something nice. Basically, that's the idea. So I will be looking at the exponents of the prime factors, right? So let me try to explain. So I will be, so basically I will be considering the 3 exponents for each integer, right? And try to understand, is it an even number or an odd number? Like the parity of each number, right? So of course, I have lots of possibilities. So if I write it down in English, then I would write all possibilities. So since I have 3 exponents, I should say all triples. All triples of exponents. But I'm only considering parity, right? So here maybe it's a little hard to understand the definition I wrote down. Like I'm saying all triples of exponents, so A, B, and C, the exponents, all triples, but only in terms of parity. This means I'm not considering that 1, 2, 3. I'm considering as the same, basically. So of course, doesn't mean anything, but in my in my focus, I'm only considering the fact that uh, parity is the same. If parity is the same, to me, the case will be the same. Like the triple will be the same because I'm only considering parity, right? So this is odd, even, odd. This is also odd, even, odd. So I will consider it as a same. So now my question is, how many such triples do we have? How many cases do we have? So I have 3 exponents. Each exponent can be either even or odd. And my question is, how many different triples do we have? Yeah, 8. Why 8? Because so number of triples is equal to 2 times 2 times 2, which is 8. Why? Because this is the 2 cases I have for the first exponent. It could be either even or odd, and etc. for the others. So yeah, so 9 integers and 8 different possible triples. So 2 of them have to be the same. 2 integers have to have the same triple in terms of parity of exponents. Yeah. So if I write this down, so there is n1 and n2 so I'm writing down their prime factorizations, and I know that a1 and a2 have the same parity. Okay, and same for b1, b2, they have the same parity, and c1, c2 have the same parity. This comes from Pigeonhole. Okay, and now my question is it clear now that n1 times n2 is a perfect square? What do you guys think? Yeah, exactly. Because they have the same parity, if I add them, so because n1 times n2, this will be equal to 3 to the a1 plus a2, 5 to the b1 plus b2, and 7 to the c1 plus c2. And then when you add numbers which have the same parity, then you get an even number. So yeah, of course, this is a perfect square. Cool. Good. That's good. Now, I think we're good. Good to go. Good to start off. So let's do this. Let me see if I have another reminder, but probably we're good to go. Any questions, guys, on the 2 solutions we did so far? Okay. Okay, good. So actually, I will add a little reminder, which is not really a reminder, but a quick remark. And then we move to number bases. So quick remark, just before we were saying, if n divides a times b, okay, n is just any integer, okay? And if I add another, condition, that is, n and a have no common factor, have no common prime factor. Okay, so I've added this condition. So somehow we know that n and a share no common prime factor. Now my question is, what can you conclude? What do you guys think? So n divides a times b, and I don't know that n is prime, right? N is any integer, so it could be that n divides one of them, a or b. It could be that n divides both, and it could also be that n divides none of them. This I cannot know, but I'm adding an additional condition which says n and a share no prime factor. So now that I know n divides a times b and no prime factor of n divides a because they share no prime factor, then actually I will be able to conclude that n divides b. What do you guys think about it? So let's see why by using the prime factorizations of n, a, and b. Let's try and do this. So I will, this is, I think, the best way of seeing it and proving it. So let's consider their prime factorization. So actually, I don't necessarily need to use the exponents, but let's use the exponents because this is the general form. Okay, so this is the prime factorization of n. Now let's take the prime factorization of a. So of course, I need to change the names of the primes, right? I need to change the names of the primes because they have to be different. They share no prime factor, right? So Q1, right? Let me take A1 and QL, not necessarily the same number of primes, AL. Okay, that's the prime factorization of A. Now let's look at the prime factorization of B. So it's a bit long to write down 3 different prime factorizations. We could, okay, let me first finish writing them down. So for B, since I don't know, I mean, I have no condition like the one with N and A, which says they share different prime factors. So maybe what I could do is try and reuse the same primes. But since I don't really know which ones to use, I will just take other names. And they could be equal, they could be different. This I don't know. So R1 to the B1, R, okay, let's take T to the BT. Okay, yeah, this is a bit, yeah, hard to write down, right? Too many exponents, too many indices. Okay, now I know that n divides a times b. I'm just gonna rewrite it. Okay, I think when we see the prime factors written, we directly understand why this is correct. So we said that no prime factor is shared between n and a. Well, basically, this means all those and all those are 2 by 2 distinct. No prime factor is shared. So every P is different from every Q. Basically, this is what it says. For every I and every J. Okay. But then if I want n to divide a times b, because this is what I know, n divides a times b, then I need to find those prime factors. I need to find them somewhere in the product, which is here. Because otherwise, if I don't find them in the product, remember they're building blocks. If I don't find the building blocks in the product, this means the divisibility is wrong. Okay, but I will not be able to find them in the first part because none of them are equal to any Q. So basically this says the first part is something you need to forget. Why? Because no prime factor P will be found in this box. So this means the only box where you will find those prime factors is the second one, which is equal to B, right? Yeah, basically this is what I'm saying. If you want to find a prime factor, for example, P1, you will not find it in the first box because they share no prime factor. So you will have to go to the second box to find it. It's exactly this. And I probably cannot explain better, but still tell me if it's not okay. Just let me know if it's not clear. So so for any I, Pi to the alpha I has to appear in R1B1, RTBT, right? So why is this? Because Pi to the alpha I has to appear somewhere in A times B. Because we said the whole product divides A times B, so every part, every factor, every factor Pi to the alpha I has to appear somewhere. If it's not in the first box, it has to be in the second one. That's the idea. Okay, so we'll discuss this again in the next lectures. Now let's discuss number bases now that we have said all this. So number bases. So what do you guys know about number bases? Oopsie. Okay, so what we use usually is base 10, of course. This is the first thing I need to tell you, that the numbers we use and how we write. So it's not about the number we use, because the numbers we use are just numbers, right? 1, 2, 3, 4 are just numbers, but it's the way of writing them that will change. But the numbers will stay the same, of course. It's just how you write them down. So in base 10, for example, 56 is just 56. And usually when we write down a base representation, we use this this way of writing. Sometimes we also put the 10 as an index. Yeah, so this is just the base we all know about. So what does the base we all know about mean, actually? This is just saying that if I take a number n, so let me write this down properly. So let n be any positive integer. There is an only representation so n will be written as ak times 10 to the k, ak minus 1 times 10 to the k minus 1. And we just keep going until a1 times 10 plus a0. Basically, that's the idea. And then this means I can write down in base 10 my number using the digits that I will find in this representation. So this is the number in base 10. Okay, so here it says that it's unique, right? So you cannot have two representations in base 10 of the same number. Okay, it has only one, of course. I mean, this is the base we use always when we write down any number. So this you know already, and that this exists. Well, of course it exists. So yeah, this is what base 10 means. So now I can write down this same definition in any base. So notice that the only thing which will change is the 10, which is here. Okay. Let me write it down. So I will write it down for base B. And B is any positive integer. Okay. I will take it at least 2. Otherwise, it doesn't make any sense. Okay. So I take n to be a positive integer, and I will write down n in base B. So it says exactly the same thing. There is a unique representation. So now n will be written as ak times, so k is just an index, like the largest index here, but I'm not using always the same, of course. I'm just saying it's any index. I don't know its value. It's just a way of writing it down. So in every specific case, we would have to find the value of k, but here it's just a way of writing it down. Okay. So now the number here is not 10 to the k, but b to the k. Okay, and I keep going. A1. So I'm sure you guys are all or almost all familiar with base 2, where the digits are only zeros and ones. Okay. Oh yeah, sorry. Something I forgot to write down here is that the digits are all between 0 and 9. Of course, they are digits, right? So this is not surprising. But when you take another base, it will be a bit surprising, maybe, that the A's have to be between 0 and B minus 1. So B can be larger than 10, right? So they're not digits anymore. They could be bigger than 9 without any problem, right? It's just that it's a digit in base B. We will not use digits because the digits we know stop at 9, but those stop at B minus 1, right? In any base B. Just a bit weird, but okay. We'll look at examples just after. Okay, now let's explain where does this expression come from. So let's try and understand this expression. And you will see that it's actually just lots of divisions. Like it's the division algorithm, which is repeated. Let's see why. So maybe before we look at specific examples, we can still discuss it in a general way, and then we'll see examples. So, okay, so let's take the first thing I will do is consider the divisibility, so division of n by b. Okay, I'm doing it in a very general case, and then we'll look at examples. So division of n by b, what did we guys say? We can just write the division algorithm, which gives n is equal to B times Q plus R, right? And what do I know about R? Well, I know that R is at least 0 and strictly less than B, because I'm doing my division by B, right? So this you guys remember. So what can you guys tell me about the representation of N, which I didn't rewrite as AK minus 1, A0 in base B, sorry. So what can you guys tell me about the representation of N? Sorry, what can you guys tell me about R in terms of the representation of N that we wrote here? Can you guys link R with this representation directly? Try to look at the expression we have here and tell me if you can make a link. What would R be equal to? Yeah, exactly. So actually what I will do is rewrite the division algorithm using some indices, some index. So N is B times Q0 plus R0. And R0 is between 0 and B, strictly less than B. So actually what's happening here is that R0 is equal to A0. Like A0 from here. Okay? Why is that? Because actually I can factor out B. So B multiplied by some number, and then the last, the remainder is A0. And this is exactly what happens here. All this is a multiple of B, right? I have B's everywhere. And then I have a remainder A0. So how do I make sure this number is the same? Well, I know that they're both less than B and between 0 and B. So this is why they are the same. This is exactly why they are the same. So now let me continue the division. But now I want to write the division of Q0 this time, and still by B. So it's going to be always by B, but this time I'm looking at Q0. I'm not looking at N anymore. So Q0 is going to be equal to B times Q1 plus R1. And of course, R1 will be less than B. Okay, so now my question is, what is R1? What do you guys think? Any idea? You can take a guess. Any guess, guys? It's probably not very easy to see why, but just take a guess. Yeah, R1 will be equal to A1. Let's check why this is correct. So what I'm going to do is rewrite N. So we said B Q0 plus R0. So if I plug in Q0 by its new expression, then what is it that I will find? B squared times Q1 plus B times R1 plus R0. So basically we're building step by step this expression, right? We're building it step by step. So here, R0 is between 0 and B minus 1, right? R1 is also between 0 and B minus 1. But Q1, I don't know, right? Because Q1 has no specific condition. So this means I'm not done. I need to make sure I continue doing this until this quotient is between 0 and b minus 1. Otherwise, this means I'm not yet, I didn't find yet the good expression of n. Basically, this is the idea. So we're building it step by step. So do you guys want to see the next step? Or actually, you guys will tell me what's the next step to make sure you guys understood. And then I'll show you how it goes without describing every step, of course. Okay, so you guys will tell me what's the next step. So division of what by what? So what's the next step? Division of what number by what number? Yeah, Q1 by B, exactly. So if I write the division of Q1 by B, it's going to be B times Q2 plus R2. And R2 satisfies what we have said. So the guess now, R2 is equal to A2, exactly. And if I rewrite N as I did just before, what I will find is B to the 3 times Q2 plus B to the power 2 times R2 plus B times R1 plus R0. And this is part of the good expression. And this term is still to be determined, basically. Yeah, this is how it goes. And then you just keep going. We just continue until, so when do we stop? We stop when the quotient is not big anymore. When the quotient is, so I'm gonna say continue. And stop when the quotient, so imagine at some index k, so I'm using k all the time. Imagine that at some index m, this will be between 0 and no, sorry, this is not correct. Yeah, I need to stop when the quotient is actually equal to 0. Yeah, this is exactly when I will stop. So why? Just because imagine at some point I'm writing my divisibility qm minus 1 is b times qm plus rm, but qm is equal to 0. Imagine qm is equal to 0. So this is equal to 0. So what happens? Well, this means qm minus 1 is equal to rm, and which is less than b, at least 0, of course. So this means in my expression, basically I will be done. Why? Because so here I will have b to the m times qm minus 1. So I'm just trying to guess the expression because it's always going to be the same, right? And then I finish with b2 r2 b r1 plus r0 exactly as we did before. But this time here, actually I have found the good expression. Why? Because qm minus 1 is equal to rm. And of course, Rm is such as the others, an element which is between 0 and b. And this is why at some point, when the quotient is 0, we are done. Okay, so guys, you understood where does the expression come from, right? Please tell me if something was not clear. I hope that now you guys understand where does this expression come from, but still, please tell me if it's not clear. Maybe I can make it a bit better by explaining again. Okay, so actually, this is what we need to look at a bunch of examples right now. So let's do it. I'm still waiting for you guys to tell me if you have any question. And then we will start looking at some interesting examples. And let me see, is this the first one I want to do? No. Okay, I will start by, I'm choosing the examples. In the meantime, you can ask any question. Not this one, not this one. Okay, we can do this one. Okay, good. So let me see. No questions. Okay, no questions. So let's start looking at our examples. So first example, I will just simply ask you guys to give me the representation of some number. So this number, I will take it in base 7, and I want you to write it in base 5. So it's a number in base 7. I want you to write it down in base 5. So how can we do this? So first, what's this number? What is it equal to? Well, I know this is, I know it's in base 7, so I can write it down. I can write the expression. So 5 times 7 to the power, which power? 2, right? Plus 6 times 7 to the power 1 plus 2. This is the value of my number. So what's the number? What is it equal to? Yeah, 289. Perfect. So of course, it's 289 in base 10, but it's 289. And now I want to write it down in base 5. Oh, so Jeffrey, you already gave us the answer, 2124. Okay. I don't remember the answer, but probably correct. But let's explain how we found it. So I'm starting by 289, and I want to write it in base 5. So I will do exactly the divisions we were doing just before. Like divide by 5, get the first, divide by the last digit, divide by 5 again, the second digit, etc. This is what we'll do. So let's divide by 5. So basically write the division algorithm, right? So divide by 5, I get 5 times something plus a remainder. So what you're saying is that, oh, okay, so Abraham got it as well. So what you're saying, guys, is that 4 is the remainder. Well, of course, this is the case. I can multiply this by, let me count, 57. Yeah, I think so. And the remainder will be 4. So 4 is my first number. So if I write down the answer here in base 5, my first number will be 4. Okay, good. Now let's continue. I take 57, I divide it by 5, so it's going to be an 11 plus 2. So my second number is 2. And then I consider 11, 5 times 2 plus 1. So that's the 1. And then I consider 2. So it's a 5 times 0. So remember, we said when the quotient is 0, we stop. Plus 2. And this means we stop here. So yeah, you guys were right. So it's just doing, of course, the number reads that way, but it's just doing successful, the division algorithm successfully. Okay, so we got it. Now let's move to another example. Let me choose it. Okay, not this one. All right. Okay. So another quick example would be to write down this number. I mean, you can try with any number, of course, just to make sure you guys understood everything. So can someone give me the answer, and I'll let you do it because it's exactly the same way, right? Just do successful division. Actually, we could try and think ourselves so to make it a bit quicker, but the division algorithm successfully is already very quick. But we could try and think, for example, this number is less than 7 to this power. So I know that I have a little amount of numbers, and then maybe try to look at some, I mean, do the casework until you find it. But it's the best way is still to do the chain of divisions as we did. So can anyone give me the answer? So I let you guys try it later. I'm just trying to see if anyone has already the answer. 21125. Okay, cool. So please, guys, check this on your side. Okay, cool. So now another example. I'm trying to see if I want to do this one yet. Okay, let's leave this one for just after. Okay, another example. I'm looking at a sequence. So I can define it that way. Oopsie. So how should I define it? So it has some 2s, and then some 4s, and then some 5s. Sorry, and then 1 5. And this is for all n at least 2. So here, the number of 2s, I know it, and the number of 4s, I know it. So we have n 2s and n minus 1 4s. So n minus 1 of them and n of them, okay? So this is why in the first case, I had only 1 2 and 1 5 because n was equal to 1. So 1 2 0 4s 1 5. This is why. So I could have written the expression directly for any n at least 1. So I don't necessarily have to write this down, right? I just need to write this down, okay. So this is how I define this sequence. And the question is to write down every element. So write down an as the sum of 2 squares. So when I say 2 squares, I mean 2 perfect squares, like integers, of course. Okay, so let's do this. First, I need to understand what's this number an. And once I've understood what's this number, how I can express it, probably it's going to be easy to prove that this is just the sum of 2 perfect squares. Okay, let's try to express this number. An. So basically here, guys, I'm dealing with base 10, right? Because this is the regular expression. This is just base 10. Okay, so since I know I know the expression with the powers of 10, right? So maybe it's interesting to use it to compute to re-express the number. Because having n times a 2, n minus 1 times a 4, and the 5 at the end, I have no idea what the number is equal to. I just know how to write it down, but I don't know what is it equal to, right? So let's do this. I re-express everything in terms of powers of 10. So it will be 2 times some power of 10 plus 2 times some power of 10, etc. Okay, and then I move to the 4s. And of course, I'm asking you guys, please give me the exponents. I'm just giving you the structure of the number, and then you guys give me the exponents. Okay, and then we end with a 5. So of course, this one will be 10 to the 1, 10 to the 2, etc. But what are the last two here, and what are the other exponents? So please help me, guys. So this is exponent 1. And then what? It starts with 2n minus 1, I think. Okay. 2n minus 1. Because, so we know we have n of them here, n minus 1 of them here. Oops. Not containing the 5. N minus 1 here, and then we have 1 here. So in total, we have 2n digits, right? In total. So you're saying the first one is 2n minus 1. And I am not so sure. Oh, actually, yes. Actually, it's correct. Sorry. My bad. I was going to say 2n plus 1, but it's the other way around. So you're right. Sorry. So if this is 2n minus 1, this is 2n minus 2. And what's the last one here? I think it's actually easier to go from the other way around, from 1, because it starts with 1, and then it has to end by the last 4, and we know we have n minus 1 of them. So n minus 1, yeah, exactly. So this is why it's easier to go from this side. And then it's n, which is the one just after, and we continue until 2n minus 1. Good. So just to make sure I'm not wrong, I can just check. 10 to the 2 has 3 digits, and this is 3 minus 1, right? So it's okay. Everything's correct. Perfect. So I have the expression. Now let's try and simplify it. So here I can factor out 2 times 10 to the n. Okay. And I would be left with powers of 10. N minus 2 plus 1. I can also do the same with the other expression. So 4 times, actually I can just write 40 times 10 to the n minus 2, 10 to the, oh, sorry, n minus 2 here, n minus 3 plus blah, blah, plus 1. And the 5 doesn't change. Let me check what you guys are saying. Okay, yeah. Okay, now that I have this, can you guys help me simplify what's in the brackets? What do you think about what's in the brackets? How would you simplify it? So it's a geometric sum. I'm not sure everybody knows what a geometric sum is. So maybe we need to say it very quickly. So can you guys tell me in the chat if you know what a geometric series is? Basically, it's multiplying by the same factor. So here the factor is 10, right? Yeah. Anyone doesn't? I'm just trying to make sure everybody knows what this is. But tell me if anyone doesn't know what a geometric series is. It's totally fine. I just need to know. Okay. Okay, so let's just give the formula. So imagine Q is a real number. Yeah. So if I have the sum 1, Q, Q to the 2, etc., until Q to the M, then this is equal to q to the m plus 1 minus 1 over q minus 1, right? Yeah. Okay, and how do you find such an expression? I mean, how do we prove that this expression is correct? This relation is correct? There are plenty of ways to see it. Maybe what's the easiest way of saying why this is correct? Probably just the factoring, right? Q to the m plus 1 minus 1 is very easy to factor, as we said, right? We gave the factoring identities, which we could just reuse here. So Q just has not to be equal to 1. Otherwise, I cannot divide by 0, right? Okay, so now I can just continue and express this using fractions. So 10 to the n minus 1 over 9 plus 40 times 10 to the n minus 1 over 9 plus 5. And remember, the question was express this sum as a sum of two squares. So let's see why we have a sum of two squares here. How should I rewrite it to obtain two squares? So basically, I'm looking for squares. Let's see how I can rewrite it. First thing is simplify, right? So, okay, the 1 over 9, I can just put it on the side. And then I have 2, 10 to the n plus n, so 2n minus 10 to the n. Oh, sorry, it has a 2. So actually, I will keep, what can I do with this 2? Should I keep it out? I'm thinking, let's put it here for the moment. Okay, and then for the other one, 4 10 to the n minus 4t plus 5. Okay, not really helpful. For the moment, I don't know where to go. The only thing I notice is that 9 is a square, 3 squared. But then, how should I find a perfect squares in this? I'm not so sure. So let's see. Yeah. What do you guys think? Any idea over there? Maybe we should just put everything under I mean, above the denominator 9. I'm not so sure. Let's try and find out. Yeah, maybe this is something I could do, because for the moment I don't see anything. So yeah, let's do this. So twice 10 to the 2n. Then what do I have? Then I have a plus 2 10 to the n minus 40 plus 5, right? That's what happens. And now maybe it will be easier to basically construct squares within this bracket, because I know that 9 is a square. So if I construct squares within the bracket, then maybe if I have a sum of squares here, then probably it will be almost done. So something I forgot is to include the 5. And it's probably something I should do. So let's include the 5 before doing such a thing. So if I want to include the 5, all I need to do is add 45. And yeah, this is basically a plus 5. Okay. So now that I have this, let's try to construct two squares. this is what the question was asking us to do. So let's construct the squares. How would you do this, guys? I'm thinking that I should use the fact that this is 10 to the n squared. Right? 10 to the n squared. 10 to the 2n is 10 to the n squared, of course. So maybe this should be part of my square. And then how can I finish? That's a good question. Construct a quadratic. Yeah, this is what I'm trying to do. Construct a quadratic, exactly. It's exactly what I'm trying to do, yeah. Let's see if you guys have ideas. So what happened is that I simplified what I had, and maybe I should not simplify them. So I'm gonna tell you what I'm talking about. So here I had a minus 2 times 10 to the n plus 4 times 10 to the n plus 5, right? And I think separating those will help us construct the quadratics because having only one 2 times 10 to the n doesn't make me able to construct two squares. So probably it's better to leave them that way. Okay, and now you guys can tell me, how should I go? So yeah, what I was saying is that 10 to the n squared is probably a good square to use. Okay, and then what? Using the substitution. So you want to, okay, but yeah. Um, yeah. I agree with you, Abraham. So what we will do is consider the following. I'm just trying, right? If I take a +1 here, this is a square. And then if I take a +4, 10 to the n. So if I have a +4, this means I need to add a 2 squared. Okay. And like this, it would work. I just need to check nothing is left behind. But here I have a 1, a 4 that add up to 5. So this is good. And the two other terms, I have them. I have my squares, so I have everything. So yeah, these are my two squares. So let's rewrite this down as squares, sum of two squares. Ten to the n minus 1. And this is 10 to the n plus 2. Okay, there we go. Yeah, good. Exactly. Good job. So now I have one question for you. What was the initial problem statement? Prove that, where is it? Yeah, prove that we can write an as the sum of two perfect squares. So they have to be integers. And what did we do? We wrote an as the sum of two squares, but I need to make sure they are perfect squares. So what should I prove? What's the last step? So what do I want to prove? They are integers, of course. So prove that 10 to the n minus 1 over 3 is an integer, which happens if and only if 3 divides 10 to the n minus 1, and same for the other one, right? So let's prove that 3 divides 10 to the n minus 1, and 3 divides 10 to the n plus 2. What do you guys think about those two divisibilities? Are they clear? Are they not clear? Is it easy to prove? I'll let you tell me why those two divisibilities are correct. I give you 10 seconds for this. So what do you guys say? Yes, yeah, but why? I agree with you, Jeffrey. Oh, divisibility rule of 3. Yeah, divisibility rule of 3, I agree. So this means look at the sum of digits. Okay, cool. This is a good idea. Yeah, Abraham, I also agree with you. Yep. So is computing, I mean, what's the sum of the digits of 10 to the n minus 1? So 10 to the n minus 1 is going to be a number which looks like this. So it's only going to be 9s. How many 9s will I have? It's not important how many 9s I will have. I will have n minus 1 of them, but I just want to make sure you guys understand this. Okay, so this is clearly divisible by 3. Why? Because the sum of digits is a sum of 9s. So of course, divisible by 3. So this one is okay. And then for the second one, 10 to the n plus 2, that's a 1 at the beginning and a 2 at the end. And I have n minus 1 zeros, but again, the number of zeros doesn't change anything because the sum of digits is 3. So just look at the sum of digits. Here it's 3. Here it's a sum of 9s. So divisible by 3. We're good to go. Cool. Okay, it's almost time, but I want to do a last example. So we'll do it. Okay. What does the example say? So the example is, I think it's quite interesting. So we're looking at another sequence. I will define it, but for the moment, I'm giving you the first elements of the sequence. So 1, 3, 4, 5. No, sorry, I am wrong. I don't have any 5. I have a 9. I'm thinking at the same time, but maybe I shouldn't. 10. Okay, and let me explain how I construct the sequence. So here I'm looking at okay, how will I write this down? So first of all, I'm looking at powers of 3. So of course here we have more than powers of 3 containing powers of 3. That's the first thing this sequence contains. And also sums of distinct powers of 3. Okay. So first thing we have, first set, all powers of 3, and then second set, sums of distinct powers of 3. Okay. The question is to find the 100th term of the sequence. Okay, but first let's continue giving the first elements. So 1 is a power of 3. It's 3 to the 0, right? then another power 3, then I can add them up. So 1 is a power 3, 3 is a power 3, and then, so 2 is not possible. Then 4 is 3 to the 0 plus 3 to the 1. 5 is not possible. Why? Because if I write down 5 as a sum of powers of 3, I would need 3 to the 1 plus 3 to the 0 plus 3 to the 0, but we said they have to be distinct. So this is not possible. Okay. And then if you check 6 until 8 doesn't work, and then 9 is a power of 3. Then I have 10, which is 3 to the 2 plus 3 to the 0. Can I have 11? No. Can I have 12? Yes. 3 to the 2 plus 3 to the 1, etc. Okay, so I think you guys understood how the sequence is constructed. Now I need to find the 100th term. So let's do it step by step. But my first question to you is, can you translate basically what elements do this sequence contain? Powers of 3, okay, and sums of distinct powers of 3. So how can I express this in a good way? That's the question. Because saying powers of 3 and sums of distinct powers of 3, this is horrible. This is very hard to understand. This is a very long definition. I would like to translate it to some simple definition. So since I'm talking about powers of 3, probably using base 3 would be very interesting. So let's try to understand what this means in base 3. Okay, so let's look at base 3 and we'll try to understand what this means in base 3. So in base 3, remember, any number can be written as ak 3 to the k, and you keep going. Okay, remember this? And every digit is between 2 and 0, right? So either 0, 1, or 2. Okay. And I am considering, first of all, powers of 3. So some element of the form 3 to the k. Okay. And second thing is sums of powers of 3. So something like this. Okay. But the problem is the powers of 3 have to be distinct. All right. So those are the two types of numbers I include in my sequence. And my question to you guys is, what special thing do those numbers have in base 3? That's my question. Can you guys tell me what's special, how special are those numbers in base 3? So this number that I wrote here is AK, etc. until A0 in base 3. So I'm asking you guys, what's the expression of those numbers in base 3? So a power of 3, how do you express a power of 3 in base 3? What's the expression of the power of 3 in base 3? So if 3 to the A is hard to imagine, just give me the expressions of any power of 3 that we know. So what's 3 to the 2? Yeah, so it's 1, 0, 0, exactly. Because I have a 1 So why? Just because this is 1 times 3 to the 2 plus 0 times 3 to the 1 plus 0. So this is why, right? If I only have 1 power of 3, then I have 1, 1, and then zeros. So same for 3 to the a. This is 1 times 3 to the a plus zeros. So this means the expression is going to be 1 followed by a lot of zeros. How many zeros? A zeros. Okay, so this is the expression of 3 to the 8. Good. Now what's the expression? Yeah, it's like binary. So can you say again what you mean by it's like binary? And maybe before this, let's give the expression of the second type of numbers in base 3. So that's, we said, is a 1. So I wrote it down already, so I'm not going to write it down again. Jeffrey's saying it's like binary, but maybe when we write down the second expression, we will understand why this is interesting. So this was for the first type of numbers. For the second type of numbers, imagine that I can order the numbers like AM bigger than, I'm ordering the exponents, okay, because we know they're distinct. Remember, the exponents are distinct. So since they're distinct, then I can order them with strict inequalities. Okay, and so what's the expression in base 3? What will it look like? So the expression in base 3, basically it's a 1 times 3 to the a1. Sorry, you need to start by am. And then I will have zeros. Okay. Until I reach 3 to the am minus 1. Okay, tell me if you guys understand this. So I have zeros in the middle because there are powers of 3 in the middle, but I'm not taking them into account. So zeros. And then another set of zeros until I reach the next power of 3, and then I will have a 1. Okay, and then a set of zeros. Okay, so I continue until I get to 1 times 3 to the a2, another set of zeros, and 1 times 3 to the a1, and then I stop. So actually I don't stop because the base 3 expression goes until 3 to the power 1. So actually I continue with a list of zeros. All right. So first of all, let's see if you guys understand what I did here. Maybe I can give you an example, let's say more concrete. So 3 to the 5 plus 3 to the 2 plus 3 to the 0. So this is 1 times 3 to the 5. There is no 3 to the 4. There is no 3 to the 3. There is 1 3 to the 2. And, okay, I should have written it somewhere else. Sorry. Okay, so let's do it again. 1 times 3 to the 5. 0 times 3 to the 4. 0 times 3 to the 3. I hope you guys got it. Otherwise, tell me what's not clear. 1 times 3 to the 2. 0 times 3 to the 1. And 1 3 to the 0. Yeah, it's like binary, exactly. So actually 3 to the 0 is just 1, right? So it's like my last number. Yeah. So did you guys understand? So what will be the expression here in base 3? So down here, it's going to be a 1, a 0, 0, a 1, a 0, a 1. Okay, that's the expression I have here. And up there, it's going to be the same thing. 1, some zeros, 1, some zeros, 1, some zeros, etc. And at the end, I have zeros. So what's so special about those numbers in base 3? Can you guys say it? I mean, describe it. Anyone? So basically, I'm looking in base 3, and I'm saying either I have a 1 in the beginning and zeros, or I have a list of ones and in between some zeros. So basically, I'm considering all numbers in base 3 that what? Complete the blank. What do those numbers satisfy? So I'm guessing it's not clear because nobody's answering. So what did we say? We say we have two different expressions in base 3, but if we try to understand what makes those expressions special, I'm just asking you to express a way of generating all those numbers. So I look in base 3, what numbers should I keep? What numbers shouldn't I keep? So I'm telling you, try to define those numbers in a simple way. What should we say? In base 3, keep the numbers that are blah, blah, and don't take the numbers that have blah, blah. What's this blah, blah? Can you guys help? So you're saying keep 0, 1, 2. What do you mean keep 0, 1, 2? What do you mean by 2, actually? Because here I cannot see any 2. Like in base 3, as we said before, the digits can be either 0, 1, or 2, right? But here, I'm asking you, what's so special about those numbers? So choosing either, yes, exactly. Yes, exactly. So what I'm saying, what I wanted you to say, and Abraham, you understood. Basically, I'm telling you, in base 3, keep numbers that have digits 0 or 1. No digits is equal to 2. But in base 3, a lot of numbers have digits equal to 2. But I'm only considering those who have digits equal to 0 or 1, because the powers of 3 are distinct. If the powers of 3 could be equal in the sum, then a digit 2 would appear in the expression. But here, I'm only considering zeros and ones. Yeah, exactly. If we only have zeros and ones, then no power is repeated. So if I write down the definition of those numbers, basically take all numbers with, so take numbers that can be written with only zeros and ones in base 3. Okay, so only zeros and ones. And this assures us, as you said, that no power 3 is repeated. And at the same time, this is exactly the list of numbers we have in our sequence. Perfect. Okay, now I still need to look. The question was find the 100th term of the sequence. Now I know that it's actually binary because I only have zeros and ones. So now the question is, how should I find the 100th? And here maybe it becomes a bit tricky because the thing is that since we've used only zeros and ones, this means basically we're writing numbers as we would do in base 2 with only zeros and ones, right? So imagine I'm considering this following number in base 3, okay? And I would like to know what element of the sequence is this? So which, if it's the nth element, what's n equal to? Okay? So of course, this one is an element of the sequence. Why? Because it's in base 3 written with only zeros and ones. I'm saying, imagine it's the nth element of the sequence. Can I know what n is equal to? It would be very nice. So the thing is, since I'm considering only zeros and ones, I could translate them in base 2. So if I translate them in base 2, then imagine I just rewrite the same number, but this time not considering base 3, but base 2. Then now I can assure you that this is equal to n. Why? Because my first element is 1, remember? So my first element will be this one. So if I translate it to base 2, this is equal to 1. So this is equal to, it's the first element, right? Now if I look at my second number in base 3, it's going to be 1, 0. So if I translate it in base 2, in base 2, I will be covering all numbers. This is the idea. Because every number in base 2 contains only zeros and ones. So if I just rewrite it in base 2, I'm considering all numbers. So this is why it's actually a numbering, because I'm considering all numbers in order, right? Yeah, exactly. Yeah, I'm just converting the expression I have in base 3 in base 2, because in base 2, I only use zeros and ones. This means I'm actually covering all numbers. So if you cover all numbers, this means you cover 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this means it's a numbering. So this is why if I keep going, I will have found all integers, right? So the idea here is that having only zeros and ones it's a bit tricky. I agree. This means that I'm covering all numbers in base 2. So the base 2, translation of the number is actually a numbering. So in general, what I would do is try to find the expression of 100 in base 2. Once I have the expression of the number in base 2, just translate it to base 3. And there you have your 100th element. You got 981 in base 10. Okay, you mean this number is equal to 981. Okay, this is what you mean. Can you give us the expression base 3 or 2? Okay, thank you. So 1, 1, 0, 0, 1, 0, 0, right? This is it. Let me check. 2 to the 0, 2 to the 1. So that's a 4. Wait, 0, 1, 2, 3, 4, 5, 32, 64. It sounds like it's correct. Yeah, it's correct. Thank you. Okay, so now I just translate. And then you just compute this in base 3 and you find 981. So this is our 100th element. Perfect. So what's important is that if you have only zeros and ones, then in base 2 you're covering all numbers. If we had zeros, ones, and twos, in base 3 we'll be covering all numbers. That's the idea. Okay, we're done here. It's already time since a long time, so let me stop and enjoy the problems. So guys, I think you can take 7 minutes of break and see you back here at 9. See you guys.